Hey, welcome back everybody. I know it's been a while since I've put a video out. I've been super busy with a lot of stuff, but I got something really cool. Today on my channel, I'm going to introduce you to the next video series that we're doing. This is something that I've always wanted to do. For years I've wanted to do this. I've had a lot of requests for it. We are going to build a 351 Windsor based engine, but we're going to turn it into a Cleveland called a Clevor. So basically what we're going to do is take a 351 Windsor, which is a stronger block than a 351C block. With some upgraded parts, we are going to turn that into a Cleveland engine. So I kind of want to walk you through some of the parts that we selected for this build. We do have an early 70s 351 Windsor block that we're going to blueprint and do all the machine work to. I'll get to that a little bit later and we'll talk about that. But what we have, Edelbrock has done a really good job of producing cylinder heads that are able to make your 351 Windsor basically into a Cleveland engine. So we start off with the Edelbrock heads here. This is part number 61695. It is called the Edelbrock Performer 2V head. Now they have other versions that are more racy than these, but this engine is actually going into a Mustang that's going to be driven on the street. It's going into a fastback Mach 1. So we want to keep the thing kind of streetable while actually getting as much power and coolness factor that we can out of it. So we chose the Edelbrock. Now the Edelbrock heads that we chose, they have a 60cc combustion chamber. They have a 2-inch 050 intake valve and a 1-inch 600 exhaust. So they're pretty stout. They also have an intake runner here of 190 cc's, and they flow about 265 CFMs of air at around 600-ish lift. So they actually flow 260 CFMs at 500, and then you go a whole nother 100 thousandths of lift and they only gain 5 CFM. So we really, the camshaft that we chose, I'll talk about that in a minute, we didn't really feel like we needed a 600 with cam in this thing. Plus, the springs that Edelbrock put on these, when they come loaded like this, they only have the capability of holding about 580 lift. 580 lift is maximum, and you really don't need more lift than that because they don't flow. It's kind of pointless to put a 600 plus lift cam in a cylinder head that doesn't flow up there. In fact, the cam selection process really depends on the flow rate of the heads, and I'll talk a little more about that in a minute. But first of all, let's go down to the lower end, and I want to talk to you about what we got here. We actually bought this kit from Scat. So we've got a really stout Scat 4340 H-beam rod. We want the bottom end of this thing to be really stout. These rods will take well in excess of 1,000 horsepower. This engine isn't going to be anywhere near that. One of the things that I personally like to do is let's make the bottom end totally bulletproof with parts that are capable of handling way more power than we're ever going to make, and that way we're never going to break anything. That's kind of my philosophy. So these are a full floating bushed piston pin, and it is a 6-inch 200 thousandths long rod, so it's a longer rod than normal. It's a pretty long connecting rod. The balancer, we also went with a Scat balancer. Now we're going to go externally balanced on this one because of budget constraints. You can go internally balanced with the crank that we purchased, and I'll talk about that in a minute. However, this engine is a stroker engine. It's going to be a 408 stroker, so it has a 4-inch stroke on the crank. And the RPMs on this thing, we're not going to really see much over 6,000. It's going to redline at 6,000, and I'll talk to you about how we figured that out too. So we figured to save some money. The balancing gets really pricey when you go internally balanced on these because they actually have to put a lot of heavy metal in the crank, and that starts getting really expensive. So since the RPM is not going to be up in the crazy range 7,000-8,000, we just decided, you know what, let's go externally balanced. It'll be perfectly fine. It is going to have a top loader 4-speed, so we've got our flywheel here that is also externally balanced, got the weight on it. This is an aftermarket flywheel that has a bolt-on weight that the balance shop can trim or add to or whatever. So it's a pretty cool deal. So that is going to bring up the bookends or the ends of our crankshaft. Then we have a Scat 4340 forged crank. It's 351W. The part number is 351W-400-6200R, and it is a forged crankshaft that has a 4-inch stroke. So the 4-inch stroke crank is going to turn our 351 into a 408 cubic inch stroker. Now, the pistons themselves, we didn't want to skimp on this. We went with a Mahle piston that is the X-brace design, and of course it's a forged piece with thin rings, so we got really low tension rings, really lightweight pins, and it is the correct stroker piston pin compression height for our 408, so it'll fit right in the deck height of our 351. So a very nice piston. It has a 26cc dish. We needed to put a 26cc dish here to get the compression ratio that we're looking for. So again, this is going to be pretty much a daily driver, this car. This is the guy that owns the car is a buddy of mine, and this is his baby. He's had it for years, and he wants to be able to drive it. He doesn't want to have to run race gas or anything like that in it. So with a 60cc combustion chamber on the head and a 4.030 bore, along with our 4-inch stroke, we determined that to get about 9.7, 9.8 to 1 with a 20 thousandths gasket that we're using, we needed a 26cc dish here, and that gives us about 9.8 to 1. So I won't walk you through the math on that. I've got other videos where I'm doing compression ratio, but it works out to about 9.8, which is good. So he'll be able to run pump gas in this thing with no problem at all. So that's the piston, and I'll post the part numbers for all of this stuff below, you guys, so that if you want to duplicate this build, you can. Now let's talk about horsepower. Well, the 351 Cleveland, the 4-barrel version, was rated at about 285 horsepower from the factory, which is by today's standards just like, oh my gosh, that's terrible. You know, we have factory cars making 500-600 horsepower nowadays. So we ran the numbers, and the numbers actually, even with all of these parts, don't seem super impressive, but they are if you think about the fact that this motor made 285 horsepower in the 4-barrel version from the factory. So we figured a couple things out here as far as horsepower. Now, the CFM flow of the heads is key to horsepower. So we know that so we look at the flow numbers on these heads, and I looked them up. These heads flow about 265 CFMs at 600 lift. They flow around 500 lift about 260 CFMs. So we only gain 5 CFMs for moving that valve another 100 thousandths. It seems silly to do that. So the camshaft that we chose is a Howard's. It's a CL220325, which is a hydraulic roller. It's got the tie bars on it. It's not the roller that uses the factory spider assembly. We decided to go with the tie bar setup. So this camshaft has 560 intake lift with a 1.7 rocker, and it has 565 lift on the exhaust. The duration, I wrote all this down, on the intake is 225 at 50 and 233 on the exhaust at 50. So this is what we call a dual profile cam. Now let me explain to you why we chose a dual profile cam. I get a lot of people say, what cam should I put in? I mean, there's so many options. What do I pick? Well, the lift of your cam, whatever your cam lift is based on cylinder head flow. So I talked earlier about the fact that these cylinder heads flow 260 CFMs on the intake. From 400 lift to 500, I'm sorry, take it back. From 500 lift to 600 lift, we gain 5 CFMs. That's not a lot of gain. So it would not be beneficial to put in a 600 lift cam, mainly because you're compressing that spring another 100 thousandths Well, it takes horsepower to compress those springs. It doesn't make sense to compress the spring all the way to 600 thousandths and exert energy on the cam when you gain only 5 CFMs. So normally what we'll do is we'll back off the lift a little bit from there, right? It is possible that you can put way too big of a lift cam in your head. People do this with stock heads all the time. They got stock small block Chevy heads that don't flow at all, and they go out and buy a 600 lift cam when those heads only flow to 450. That's foolish to do that. That's the wrong camshaft for that engine. So the flow characteristics of your cylinder heads, you guys, is what determines the lift of your cam. So our max lift is at 600, our max flow, sorry, is at 600 lift on this cam. We picked a cam that has about 550 lift, right? So we backed it off from 600 lift, and we got about, at 550 lift, we got just a couple CFMs less than what we had at 600. So it makes sense that you want to get up there on the range, right, where the max flow is, but you don't want to go all the way to the top, and you don't want to exert too much energy. So we'll back it off usually about 50 thousandths from whatever the max flow point is, especially if we're not gaining a lot between 5 and 600 lift. I hope that makes sense. So, and as far as the duration goes, now the duration on this cam is 225, 233, and the RPM range of this cam is rated between 2200 and 6600 RPMs. We determined based on the stroke, and they use the same cam in a 302. In a 302, you would probably be twisting this thing to 6600 RPM all day long. We determined that with our 4-inch stroke, our piston speed was going to be too fast at 6600 RPMs. What we like to see is, and hopefully you're catching what I'm doing here. I'm trying to tell you how to select your cam. What we're doing when selecting the duration is the duration of your cam controls the RPM operating range of the cam. So this camshaft that we chose has an RPM range from 2200 to 6600, right? And it's a little above where we want to be, but that's fine. It'll operate fine to 6,000. We're going to redline this engine and say we want no more than 6,000 RPMs. And the way that you determine that is by piston speed. So a good rule of thumb, if you want something to live for a long time and you want a real safe RPM, is you say, I don't want my piston speed to be, my average piston speed to be more than about 4,000 feet per minute, right? So the way we do that is we take the stroke and we multiply it by the RPM, and then if you take that number and you divide it by 6, so in other words, stroke times RPM divided by 6, it's going to give you your average piston speed in feet per minute. How many feet per minute is that piston traveling? Well, 4,000 feet per minute is not really a super high speed if this thing was just going in a straight line, right? But remember, the piston's not going in a straight line. It's coming up to the top and stopping and changing direction and going down to the bottom and stopping. It's got this reciprocating thing going on. And so there's a lot of stresses and forces on the piston at the top and the bottom of the bore. And this is what you have to consider when it comes to piston speed. A lot of street rod guys will say, well, you know, you can go as high as 4,500 feet per minute. Well, yes, you can. But I like to keep things safe, especially in something that's going to be, you know, the way I build it is I want a bunch of bulletproof parts and I want it to live for a long time and make good power. So I'm going to say 4,000 feet per minute. Well, if you do the math and you take the 4-inch stroke that we're going to use and you multiply it by 6,000, right? So 6,000 RPM. So 4 times 6,000 divided by 6 comes out to about 4,000 feet per minute. Now, if you go to a higher RPM, if I say 4 times 7,000, right, you get a higher RPM. So I'll show you how this works. We'll just do this real quick. I got a calculator on my phone here. So I have a 4-inch stroke. So we're going to say 4.000. That's our stroke. And I'm going to say, how many RPMs do I want to run? I want to run 6,000. 6,000. So 4 times 6,000 is 24,000, right? Divided by 6, which is our constant, and I get 4,000 feet per minute. Now, let's say I want to run this thing to 7,000 RPMs, okay? So I'm going to go 4 times 7,000, right? Equals 28,000 divided by 6, right? That's 4,666 feet per minute. 4,600 feet per minute. That is going to put a lot of stress on those pistons and rods and crankshaft and so forth. If you want it safe, I'm telling you, keep your RPM, especially with these longer stroke motors, to around 4,000 feet per minute and everything will be fine, especially with the good parts that we have. Listen, a stock motor with stock connecting rods, stock crank, and stock cast pistons will run 4,000 feet per minute without basically no trouble. So with these upgraded parts, we can do that, and it's going to be very, very safe, and it's going to have a lot of longevity. Now, a lot of people say, well, you know, if you got all those high performance parts, why don't you run at higher RPM? There's no reason to. If you choose a cam that has an RPM operating range where you're at, which we did, you can make all the power you want in a lower RPM range, and it saves the motor. It keeps the motor from, you know, you're not spinning the thing to within an inch of its life. That's my take on that. All right, so that's kind of where we're at on this thing. Now, I ran the numbers, the horsepower numbers. I talked about horsepower. So the way that we get horsepower, we know that Superflow has provided some formulas for us, and we know that they work pretty good. They give us a good idea of how much power we're going to make. These heads were flowing 265 CFMs at 600 lift, right, on the flow bench, on the intake. We also have to look at the exhaust flow that corresponds to that, and we have to kind of figure that into, because everything that goes into the motor has to come out. To be honest with you, I mean, I like these heads. They're beautifully engineered. They look really nice, and they have the relocated water jacket and everything, so you can use the Cleveland style heads on a 351. It's going to be cool, you know. But to be honest with you, if you really wanted to maximize these heads, you probably would want to have these CNC ported, because the exhaust flow numbers on these heads, to be honest, I was a little bit disappointed. At that same lift point, 600, we got 265 lift on the intake, and the exhaust we have 165. So we have 100 less CFMs. And so what we have to look at when we look at horsepower is we have to look at something called percentage of flow, right? This is a thing. So I look at that intake flow and that exhaust flow, and I go, okay, what percentage of my intake CFM is my exhaust flowing? That's called percent of flow. The reason that percent of flow is important is because it is a factor in the horsepower potential of the head. We know, based on the formulas we get from Superflow, that at 28 inches of mercury or water, which is where they flow these, that's a standard for the industry. In other words, the flow bench motor is spinning fast enough to pull liquid 28 inches up a tube, right? That's how much draw it creates. Now we can change the bench flow. We can raise it to 40, we can lower it, but the industry standard is they're going to spin the motor in that flow bench to 28 inches. Or in other words, I'm going to pull 28 inches of liquid up a tube. So these were flowed at 28 inches. I looked up the numbers, and we know that at 28 inches of flow, the horsepower potential of a cylinder head is 0.26 horsepower per CFM. Okay, so let's take a look at this. So if I take my flow numbers on this head, on the intake, which is 265 CFMs, and I multiply that, 265, and I multiply that by 0.26, I get a horsepower number, right? 68.9, or we'll say 69 horsepower. Now remember, that's one cylinder. We have a V8 here, so we have to take, we'll round it up to 69 horsepower times 8, and we get 552 horsepower. So we have 552 horsepower potential from these heads. Well, that's really good considering the 351 Cleveland had 285 horsepower. But wait, there's more. We have to factor in that exhaust, right? So what we have to do is we have to figure out what percentage of that intake flow the exhaust is flowing. And the way we do that is we take our intake and our exhaust flow and we divide them to get a percentage. So we're going to take 165, right? We're going to take 165 and divide it by 265. And that gives us 64% of flow. So in other words, my exhaust port on that head is flowing 64% of what the intake flows. Now listen guys, to be honest with you, that's not really very good flow. That's mediocre. The factory heads are usually around like 55-60%. A really good CNC ported prepped head is going to be 85 to 90% of flow. That's really what you want. Now the reason that's a factor is because of this. I'll show you. So we got 64% of flow. Remember, we had 552 approximate horsepower capable of this head. But that is based on our intake CFM. Now in order to get the actual horsepower potential of this head, we have to multiply that 552 by our percentage of flow. So we're going to say 552 times 64%, and we get 353 horsepower. Now, again, the 351 Cleveland was rated at 285 horsepower with a 4-barrel on it. That was with the big heads. The 2-barrel version was like 235 or something, right? They didn't make that much power for what they were in factory form. I know some of the Cobra Jet stuff was better and all that stuff, but certainly not anywhere near 400 horsepower. Well, this is a guideline. Now, the other thing is, what we have really discovered through trial and error is the fact that this kind of horsepower potential is usually what we see on a 300 to 325 cubic inch motor, somewhere in there on the dyno. The added benefit of this engine is it's a 350. So on the 350s or 351s, we usually see maybe 10 to 15% more than this, right? Because the cubic inches, right? The flow numbers don't tell you everything. It just gives you a baseline of the potential of the head. But the other factors are the compression ratio, the efficiency of the engine, the low tension rings, the cubic inches is a big thing. Basically a 300 cubic inch engine up to a 400 cubic inch engine. So you can add probably 20% to that number. So based on these numbers, my estimation is I'm going to say this engine is going to produce really close to around 400 to 425 horsepower, which is really, doesn't sound like a crazy amount of horsepower, but based on the fact that the original 351C heads were like 285, that's a really big improvement over the you know, what you would see with like stock 351C heads. Now, if you really wanted to get crazy and get up to 500-600 horsepower with this, you could, but you'd have to buy the heads or have the heads CNC ported or step up to like an AFR head or something that flows 320, 330 CFMs and has really good percentage of flow. And then you can see some big horsepower numbers. So that's basically where we're at. I hope you guys are excited about this. This is just the introductory video. I have actually got the block clean and I've started the machine work on it. So once I get the block bored and prepped, we're going to do a pre-assembly on this, because since it's a stroker, we want to make sure that nothing hits inside. We're confident that it's not, because Scat is pretty good at relieving this area so we don't have any cam clearance problems or we don't have any block clearance problems. So most guys that put these 408s together with this kit really don't have any trouble with any kind of clearance inside, but you still have to check it. Also, we have to check everything, piston to valve clearance and all that stuff. One nice thing about the Mahle Pistons, in the old days, traditionally forged pistons, you had to run a lot of clearance and you had piston slap. Well, one thing I've discovered, I've done quite a few builds. I did a 6.0 stroker last year with a set of these very similar pistons. you can run very tight clearances with these forged Mahle pistons. They're amazing. It's like 2.5 to 3 thousandths clearance, just like a cast piston, but it's a hardcore X-brace forged piston. So that excessive clearance thing with piston slap and everything is kind of a thing of the past. That's old school forged stuff. The new forgings and stuff that they have today, the forging processes, the materials are phenomenal, right? Very low tension rings and so forth. So it's good stuff. So I hope you're excited about this. I hope you stay tuned. In our next video, I'm going to start putting this thing together, and we're going to build ourselves a 408 cubic inch Clevor. Thanks for watching. Be sure to subscribe below, and I will talk to you very soon, I promise. Now, the other aspect of the camshaft selection is dual profile or single profile. So what you'll see is you'll see camshafts that have intake and exhaust lifts so that they're the same. They might have 550, 550, and then you look at the duration, and the duration of the intake and exhaust lobe on each cylinder is, say, I don't know, 220 or 50 or whatever. So the rule of thumb for choosing either a single profile or a dual profile cam, if you go back and you look at the percentage of flow that we have on the camshaft, the percentage of flow is the percentage between the intake and exhaust. So we look at the flow numbers on the intake and we look at the flow numbers on the exhaust. If we have 75% of flow or better, we will usually pick a single profile cam. If we have less than 75% of flow, in other words, that exhaust, it's flowing less than 75% of the intake flow, we like to see a dual profile cam. And most of these dual profile cams will actually have more exhaust lift and duration. We're opening the exhaust valve a little more and we're holding it open a little bit longer. Now, the reason we're doing that is that bigger lift on the exhaust and that longer opening period on the exhaust is actually helping us to compensate for that poor flowing exhaust port, or that exhaust port that's flowing less than 75%. So 75% of flow is pretty much the cutoff as far as dual and single profile goes. So hopefully that makes sense. So there's and if you have questions on that, you can ask below, but cam selection is basically head flow for the lift, RPM range for the duration, and percentage of flow between intake and exhaust for single and dual profile. And that's basically it.